All right. Welcome everybody. Good afternoon. Let's start our lecture now. Now, in our previous discussion, we have discussed about how to use numerical methods to solve an equation of motion, right? We have introduced to you the simplest numerical methods that enable you to solve for the whole motion described by Newton's law. Now, today we are going to discuss about the numerical errors. Now, the numerical method is powerful. Namely, you can use the numerical method to virtually solve any dynamical problem. Okay, you just change the acceleration, the formula for the acceleration to cater for different problem, and you can solve virtually any problems. But the numerical method also has its drawback. The first drawback is that you cannot have an analytical formula so that you can put in the numbers to cater for all the cases. You have to study the cases one by one. And also for numerical calculation, you always involve numerical error. Okay, so we are now going to discuss about it. Now the equations for the constant accelerations is given by this. And they are only approximately correct if delta t is small. Okay, in the condition that when delta is small, the instantaneous acceleration is approximately equal to delta x over delta t, while the instantaneous acceleration is equal to delta v over delta t. But that is not exact. That is approximately correct only. So if you iterate this equation for a number of steps, there will be errors introduced in each step. And so the error tends to accumulate over with time. So after you do it for 1,000 steps, for example, the error will get accumulated. And that will be noticeable. Okay. So there's always a trade-off in doing numerical calculation. If you use a smaller delta t, you will get a better accuracy. For example, if you use 0.1 at the time, 0.1 second at a time step, probably you will get only a very crude answer, which is not accurate. But if you use 0.01 as your time step, delta t, then you will get a better result. If you are able to use 0.0001, then you will be able to get a very accurate result. But remember, if you use a smaller delta t, that implies you have to use more steps in your calculation. For example, if you calculate the motion for a time interval of 1 second, just 1 second, and you divide the timeline into 100 steps, then you have to, then the delta t is 0.01, right? And you have to do the calculation 100 times to solve the whole problem. But if you use a delta t that is much smaller, for example, 0.00001, which is 10 to the power, say 10 to the power minus 4, okay? Then you have to do 10,000 times. You have to do the calculation of 10,000 times to just finish the calculation for a period of 1 second, okay? So the trade-off is there. If you use a smaller delta t, you always get a more accurate result, but you have to use more steps in your calculation, and that means more computational time and resources. Now, normally, this is not important because we are in an age, in an era where computer technology is very advanced. Even a desktop computer will allow you to do the calculation very fast. And so this is normally not a problem. But if you have a very complicated equation and you would like to do it for a very long time, you need a very high accuracy, then this would be quite problematic. Now, we actually have introduced to you the simplest numerical scheme. Now, what we call the numerical scheme is here. Now, let's go back a little bit. Now, we use the quantity x, v, and a at time ti, and use this two formula to let's calculate the quantity x and v and a at time t I plus 1. So in advancing one step forward, we are relying on this numerical scheme. This is called a numerical scheme. Now, this is in fact the simplest numerical scheme. The simplest approximation is to approximate V by delta x over t, delta x over delta t, and A by delta V over delta t. This is the simplest approximation. And using the simplest approximation, we arrive at the simplest numerical scheme. But in fact, if you need the high accuracy, we can use a more sophisticated numerical scheme. Those schemes will not be taught in this course because they are more complicated, and you will learn it in senior year if you study physics, and they will substantially improve the accuracy, but without decreasing delta t. Okay, so that is the important thing. If you use a more sophisticated scheme, you can obtain a solution with high accuracy without using a very small delta t. And so you could use a less calculation time and resources. Now, I encourage you, because I will give you some homework to do. I encourage you to try decreasing the delta t to see what happens. Okay, and you will see when you decrease the delta t, the error will get getting smaller. Now, how do we know that something is an error? Now, I quote an example for you to understand this. Now, let us study this motion. The acceleration of the object is given by minus omega squared x. Now, if you remember this formula, you will notice that this is in fact a simple harmonic oscillation. Do you remember this formula? No. Let's go back a few slides. In our previous lecture, we discussed about this, right? This one. This is simple harmonic motion, a spring mass system, right? And we arrive at this equation, right? The left-hand side is acceleration. The right-hand side is the minus a constant, minus omega square, multiplied by the displacement. So this is the equation of motion for an oscillation, a simple oscillation. Now, if you use your Excel like this to calculate the motion, you will find the following thing happening. Now, this is a typical graph that you might get in your calculation. Now, because the oscillations conserve the energy, right? You later will learn about the conservation of energy, but I think you learn also in high school that the energy will not increase, right? The energy will maintain constant. There may be energy loss, but the energy loss is not described by this equation. There's no dissipation in this equation. So the energy is conserved. Now, so after each oscillation, the particle will go back to its initial position. Is that right? It will not overshoot the initial position. Otherwise, the energy, it means that it's oscillating with a larger and larger amplitude. The energy will increase, right? So that's not real. Okay. Now, but if you use a numerical scheme to do this, you will notice that after a cycle oscillation, the particle actually goes higher than its initial position. The initial position here is x equal to 1. But after one cycle of oscillation, the particle actually go higher than its initial position. Okay, so that does not make sense. And you just realize that this is a numerical error. This should not be real. Okay, it's introduced to in a calculation due to this approximation. Okay. Now, how do we know that? Be sure that this is a numerical error, but not a real thing. We decrease the delta t. Now, in the figure on the left, I have used delta t as 0.01. Okay, but in the figure on the right, I have used delta t as 0.005, which is half as small. Okay, so after using this delta t, which is smaller by half, I can see that there is still a numerical error here. But if you compare the two, I can see that the numerical error is smaller. If you don't believe it, you can decrease the delta t further. For example, to 10 to the power minus 3. If you do that, you will find that this discrepancy will be even smaller. And so by decreasing delta t, you know that surely is a kind of numerical error. So you should be able to distinguish the error from the real result. And you should always tolerate some errors. There's no numerical calculation that does not carry an error. Okay, so you should learn to tolerate a little bit of error, even though they are not perfect. Okay. Now, when doing numerical calculation, a common question is that what delta t should we choose? Now, you just said when I decrease the delta t, that solution is more accurate, right? But you need more computational time and resources, right? So what delta t should I choose? Do you have any reference? Is 0.1 second enough or 0.001 second enough? I don't know. Now, so let's look at the problem. For example, in the previous discussion, we have discussed about these two problems. One problem is the v decreasing with time when the object is projected into a medium, the velocity decreases with time, right? The other problem is a simple harmonic oscillation that we have just described. A particle oscillate back and forth under the action of a spring, right? Now, so for these two problems, we actually have a time scale. Do you remember what is the time scale? For the exponential decaying formula for the velocity, the exponential factor goes as e minus t over tau. So tau is the time scale. When t is equal to tau, do you remember what this factor will be? When t is equal to tau at this time, the exponential factor becomes e to the power minus 1. And e to the power minus 1 is about 37%. So that means after the time tau, the velocity has decayed to about 37% of its initial value. That is a substantial amount. So the tau actually gives us an idea of how fast the system change, right? So if you have some parameter, for example, you know the B and you know the M, you calculate tau, and you know how fast the system will decay with time. Now, because when you're using this approximation for V and A, we need to find a time interval such that the change in the velocity and the acceleration is negligible. So that means the delta t that I choose for the numerical calculation should be small, much smaller than the timescale tau. The timescale tau is the time for the substantial decay to happen. If I want in the delta t that the acceleration or the velocity doesn't change much, change very little, then I have to choose a delta t that is much smaller than tau, right? So in this case, the exponential time constant, the timescale tau, is the timescale that I must refer to. And in doing numerical calculation, I should choose a delta t much smaller than tau. Now, how about an oscillation? For an oscillation, there's a period. And a period is given by 2 pi over omega. The period and the angular frequency, they are related this way. And you can see the period is the time scale where the motion change substantially. So you should choose a delta t that is much more than the period. Okay, so that is typically what we want, what is needed for a reasonably accurate calculation. Now, for example, if the tau is 10 seconds, then what should you choose for delta t? If the tau is 10 seconds, somebody responds to me? Any idea? What is called much smaller than? Now, for much smaller than tau, you need at least 100 times smaller, right? So if tau is 10 seconds, you should choose a delta t at least 0.1 second, okay? If you do it better, you may be choosing 0.01 second or even smaller, but you should at least choose the time t that is, say, several tens or even 100 times smaller than the time scale, okay? So let's stop here for this chapter. And then now we go for a new chapter on what? Sorry, I go back on the Newton's law of motion. Now we come to Newton's law now. after discussing about a lot about dynamics and kinematics, actually we discussed about kinematics, dynamics and kinematics, sorry, and then we now involve the force, and involving the force is just the dynamic of the problem. Now, in a previous chapter, we have mentioned to you that the fundamental problem of mechanics is to solve the equation of motion. We are given an acceleration as a function of time, maybe the position of the object and even the velocity of the object. And the acceleration is given by the second time derivative of the position vector, right? And if you know this equation, if you know the functional form of A, and A is equal to d squared r dt squared, that is equation of motion, you need to solve for R. That is the fundamental problem of mechanics. And how do we know A? How do we know the acceleration? The acceleration is actually determined by Newton's law, because Newton's law of motion say the acceleration is determined by the force, right? Newton's second law says that the acceleration is the net force divided by the mass m of the object. Okay. Now, but there are three questions to be addressed, and so there are three laws of motion. Okay. The first question to be addressed is we talk about force, but how about if there's no force? If an object is not affected by any force, then how would it move? Okay. How would it move if the body is affected by nothing? That is the first question. But there is a hidden, deeper and hidden question here. In general, instead of just asking what would the object move if it's not affected by force, the hidden question is that which observer can measure the motion and apply the Newton's law? Okay, because if you measure the motion of the object, you have to have a reference. For example, you measure the motion of a cat relative to you who are at rest in the room, right? So your reference is a person that is at rest on the room. Okay, so you need a reference. So which observer are legitimate to make such measurement and applies the law of motion to describe the motion of the cat? That is a question. Now the second law is familiar to you. Now this is of course Newton's first law. The second law is of course familiar to you. How would the object move if there's a net force applied to the object? And Newton's second law says the net force will produce an acceleration, right? And that is Newton's second law. The third law concerns with interacting body. If two or more bodies interact with each other via their forces, then how are the forces related? If A exerts a force on B, then B simultaneously will exert a force on A. So how are the two forces related? Newton's third law told us that the two forces are equal in magnitude but opposite in directions, right? So that is Newton's third law. Now, so we will discuss about the three laws applied to a body and also a system of interacting bodies. And in this chapter, we will ignore rotation. That means we only consider the body to be moving as a whole in translational motion. We would not consider the rotation of the body. The rotation of the body will be discussed in chapter 6, in the chapter of rotation. We have a separate chapter, a separate long chapter to discuss about that. Now let's talk about Newton's first law. I think you all know about Newton's first law. But I just want to challenge you with some conceptual subtlety about Newton's first law. Now, Newton's first law says that a body will either remain at rest or in uniform motion unless it is acted by a net force, right? Now, I know that if there's no force acting on the body, or the net force acting on the body is zero, then the body will be either at rest, remain at rest, or remain moving uniformly. Now, that is a condition on the body that are not affected by force, but we also need another condition. The condition is that we need the condition to be imposed on the observer. Who determined whether the body is at rest or in uniform motion. That is the question, right? Now, if the observer himself is not at rest, then I will ask a question. If the observer himself is not at rest, then would he be the right observer to describe the body? Will he be able to apply the law, the first law of motion to that body? That is the question, right? So we need another condition to be imposed on the observer also. It happens that the observer himself must be also in rest or in uniform motion. Otherwise, he would not be able to apply the law to describe the motion of the body. Now, why? Because you imagine an observer is accelerating, then what will happen? Now, suppose you have a bus, and inside the bus, you have a person standing inside, and the bus is moving with an acceleration relative to the ground. So you just get a ride on the bus, and the bus start accelerating to the right. Okay. Now, when we look at an object on the ground, we find that the object is rest, right? But what would happen if I look at this object from the point of view of the observer inside the bus? Now, for the observer inside the bus, he will be seeing all the object and also the ground accelerating in the opposite direction. For an observer inside the bus, he will not be seeing himself accelerating. He will just seeing himself and all the object in the bus to be at rest. But when he look outside the window, he will find that all objects, including the ground, will be accelerating in the opposite direction to the bus. But of course, that acceleration is not real, right? Now, he sees an acceleration, but the object here is not acted by any net force. There is no force acting on the body to the left, right? So this observer is not a good observer, because if we apply Newton's second law to this body, he will wrongly conclude that this body is subjected to a net force, which is not correct, right? So an accelerating observer is not the right observer to apply Newton's law. He cannot apply Newton's law in this way. Okay, so you need some condition to be imposed by on the observer. Now, suppose you have two spacecraft. They are traveling in opposite direction, and in one spacecraft there's Einstein, and in another spacecraft there's Newton. The two spacecraft are traveling in opposite direction, and they are moving with uniform velocity. Now, the important thing is that they are moving with uniform velocity. The velocity doesn't change with time. So what will happen? Now, if I'm Newton, I am at rest inside this spacecraft, I will not feel myself moving, because according to Newton's law, you don't need any force to maintain a uniform motion, right? So Newton will not feel himself moving. He will feel himself just at rest. And he will see Einstein moving towards him with a certain uniform speed, right? But if you are Einstein sitting on his spacecraft, you will feel yourself as at rest, just like Newton. And you will see Newton's spacecraft moving towards you with the opposite velocity, right? So there's no method for me, for Einstein or for Newton to distinguish which spacecraft is moving and which spacecraft is at rest. So that means what? That means uniform motion is relative. There's actually no real difference between uniform motion and at rest. In the frame of reference, in the reference point of Newton, he will see he's at rest, but Einstein is moving at uniform velocity. But in Einstein's point of view, Einstein is at rest and Newton is moving. There's no way for us to distinguish who is moving or who is at rest. Even if they do any experiment on the spacecraft, they cannot distinguish between who is moving and who is at rest, as long as they are moving with uniform velocity. Okay. Now, so the important thing is that why can't they distinguish themselves from being in motion or rest? Because no force is needed to keep a body at rest or moving at uniform velocity, right? So there's no real distinction between at rest and uniform motion. Now the philosophy behind is that uniform motion is the same as at rest. They are the most natural state of motion. They need not be explained. So any body which is not affected by anything will be maintaining its motion at rest or uniform motion. Okay. So what Newton's first law means is that when a body is not affected by force, the object is in that natural state of motion. And in order to apply this law, the observer who sees the object must also be in this natural state of motion. Okay, the observer himself cannot be accelerating or decelerating. He must be either at rest or moving at uniform velocity also. Okay, so that is the important thing. Now, so Newton first law defined what is called the inertial frame of reference. Inertial frames of reference are observer moving relative to each other at constant velocities. And Newton's law is said to hold relative to the inertial observer only. Okay, so when you want to describe the world, the motion of the world with Newton's law, you yourself must not be accelerating. You yourself must be in an inertial frame. Okay, and inertial frame means you yourself is either rest or in uniform motion. Okay, now this law is founded by Newton and Galileo for the laws of mechanics in the 17th century, but later in the early 20th century, it is generalized by Einstein to formulate the principle of relativity. Einstein actually extended this law to all laws of physics. Okay, Einstein think that the inertial frame of reference is for inertial observer, they can describe all laws of physics. Now, for non-inertial observer, I have such experience for you to share. Now, if you are inside a bus and the bus starts to accelerate, you will feel yourself as being pulled back, right? That is a so-called inertial force. The inertial force is in opposite direction to the acceleration. If the bus accelerates forward, you feel yourself to be pulled backwards, right? And you feel yourself to be exerted by a force backward in opposite direction to the acceleration. And that's called the inertial force. Whenever you feel this inertial force, you feel, you know that you are yourself is accelerating. Now, the inertial force is not a real force. It is only the reflect the inertia of your body, because your body does not want to be accelerated. Your body has inertia to acceleration. So when the bus starts to accelerate, your body tends to fall back. Okay, so it's not a real force, but you have such a feeling that makes you know that you are not in an inertial frame of reference. Now then we would like to discuss about Newton's second law. Newton's second law says that the net force acting on a body is equal to the body mass times its acceleration. Now we have the two terms here to be defined more clearly. The acceleration, I think you know, we have defined it very clearly, but how about the force and the mass? Now the mass is the inertia of an object. It is a reluctance to change the body state of motion. Okay, so the larger is the mass, the more reluctance is the body to change its motion. So you need a larger force to produce the same acceleration, so to speak. When you compare a small mass to a large mass, when they are being applied the same force, the smaller mass will have a larger acceleration than the larger mass. So that means the larger mass is more reluctant to be moved by the force. Okay. And the SI unit of mass is kilogram, and acceleration is meter per second square. And so by Newton's second law, the force is equal to the mass times acceleration. So it carries a unit of kilogram meter per second square. And we define the force, unit of the force to be 1 Newton. 1 Newton is 1 kilogram meter per second square. Now, when we talk about the mass in Newton's second law, we are actually talking about the inertial mass. Now, what is meant by inertial mass? Inertial mass means the mass defined by measuring the acceleration when certain forces apply on a body. Now, let's take this example. Suppose we have a standard mass. The standard mass may be a standard mass in Paris laboratory. That mass is a standard 1 kilogram. Nowadays, we are using a different method to define the mass. But anyway, let's assume that we have a standard mass. This mass is 1 kilogram. Okay. And I call this mass ms. Now I apply a force on the mass. I apply this force, say by using a spring. When the spring has a certain extension, the force is equal to F, say. So the mass will be accelerating by the force, right? And I assume that the acceleration is AS. Now let us apply the same force. The same force can be adjusted because when I know a specific property of a spring, I can always use the same extension of the spring to produce the same force. So I can adjust my extension to adjust the force applied on the body. So I'm using the same force now, but I'm pulling another object. And the object, this elephant has an unknown mass ME. This mass I don't know. But I found that this elephant is accelerating by with AE, okay, with acceleration AE, which I can measure. Now, both acceleration I can measure. I can measure AS and AE. And I know that they're acted by the same force. Okay, even if I don't know the force, I can use these two equations to eliminate F so that I got ME equal to AS over AEMS. And that means after measuring the acceleration of the two bodies under the same force, I will be able to calculate the mass of the elephant with the standard mass, with the making reference to the standard mass ms. Okay, so this is what I mean by inertial mass. I can define the mass of the body by measuring its acceleration when a certain force is applied onto it. Now, of course, this is not a real experiment. Nobody will do the experiment to determine the mass. Okay, but conceptually, you can do this. And if you conceptually do this to define a mass, that is called the inertial mass. Now, there's also another kind of mass called gravitational mass. Now, what we normally do to measure the mass of the body is to compare the force of gravity acting on the body. For example, when we have a beam balance, this is a balance. If you put some weights on one side and we put and the object with mass m to be measured on the other side, if the two sides are balanced, then the mass of this object is equal to the sum of the weight here, right? Now, here we are comparing with what? We are comparing the gravity force. When the gravity force acting on the two bodies are equal, right? The balance, the level will get balanced. So we now in this situation we are comparing the gravitational force. So the mass of the body that gives rise to the gravitational force is called the gravitational mass. So gravitational mass is conceptually different from inertial mass. When we say the gravitational mass, what we mean is that the mass that generates the force of gravity, the mass that interact with the gravity force of the Earth and generate the weight of the object. That is what we mean. Now, but it just happened in Newtonian physics that the gravitational mass and the inertial mass, they are equal. Okay, they are conceptually different, but they are equal in magnitude. Newton do not know why, Newton simply says that the inertial mass is also producing force of gravity. Newton do not answer this question. But later, when it comes to Einstein, Einstein actually understand why the two masses are equal. He understands the two masses are equal based on the so-called principle of equivalence. And that principle forms the basis of general relativity. I will not discuss about general relativity in this course, but I just want you to know there are two kinds of mass, and what we are talking about is the inertial mass, which is different from the mass that generates the force of gravity. That is the gravitational mass. Now, suppose we now apply a force on the elephant, and its acceleration is A. And how about if I use the same spring and I now apply 2 springs on the elephant? I'm producing a force of 2F. What would the acceleration? According to Newton's law, the mass of the body doesn't change, so I expect the acceleration to be double, right? And so if I use 3 springs, then I would be getting 3 times the acceleration. So in this case, the force and acceleration are proportional to each other. Okay, so that's how we know about Newton's second law. Now, in dealing with Newton's second law, we also are involved with the concept of net force. What is net force? Net force is actually the vector sum of the force acting on the body. Now, Newton's law actually is given in the vector form. You can see from this equation, I put a vector sign on both sides, right? I have a vector sign on the force and a vector sign on the acceleration. And that means the force and the net force and the acceleration, they are in the same direction. The net force in that direction will produce a net acceleration in that direction. Okay. Now, and then when the net force is 0, either there's no force acting on the body or the force acting on the body are balanced, then we have acceleration being equal to 0. So the body is either at rest or in uniform motion, right? And that reduces to Newton's first law. However, we must be careful not to interpret Newton's first law as a special case of Newton's second law. Because for Newton's first law, we also impose a condition to the observer. And such a condition defines the so-called inertial frame of reference. Newton's first law says that the object to be described and the observer himself must be at rest or in uniform motion. They must be both at rest or in uniform motion. So that also defines a condition on the observer. We must not meet that. We must not neglect that. So Newton's first law is not just a special case of the second law. Okay. Now, how do we find the net force? These are high school physics, but I just want to have a brief review with you to make sure you understand the basic thing. Now, only the force exerted directly on the body is included, not the forces acting on other body. That is called the net force. That is called the force that make up the net force. Now, in finding the net force on a system, we use the free-body diagram. We isolate one body or several bodies from the rest of the world, and we draw all the force acting on that body or the system or that system of body. Now, this is an example. Suppose we have 2 blocks interacting with each other, and now I exert a force F2 on object B, and I exert a pulling force F1 on object A. Okay. Now, so if I isolate object A from the rest of the world, I would be able to ask a question: what are the forces acting on A, right? I would find 2 forces. The first one is, of course, the force that is directly acting on A, and that's F1. But there's another force. The other force is due to the interaction of A and B. So this force I call FAB. FAB means the force acting on A due to B. But this force is not necessarily equal to F2. They might be different. The force acting on the body B may not be equal to the force acted by B on A. They may be different. So when I isolate body A to form a three-body diagram, you cannot include the force F2 as a force acting on A. Okay, you should count count only the force that are in direct contact with A. Okay, so those two forces include the force F1 and FAB only. Okay, and after finding the forces acting on the body, we can find the net force by using a vector sum. We can use a vector sum of F1 and FAB to find the net force. Now we have a system. We have external or internal force. Now these are the words commonly used in physics. Sometimes we call a force an external force, and sometimes we call an internal force. How do we define it? Now, to define what is internal and what is external force, we first have to define a system. A system may consist of one or more objects. Okay. And the force coming outside from the system is called the external force, while the force acted between the object within the system, they are called the internal force. And in applying Newton's second law, the force and mass refers to the external net force and the mass of the system. Okay, now let's have an example. Suppose the two blocks here are connected by a string, and the string is taut. And the block M1 is being pulled to the right by a force. I call this force F. Now, so what is external force and what is internal force? It actually depends on the choice of your system. If we choose to define a system as the block M1 added to M2, if we define the system as the two block as a whole, looking at the two block as a whole, then the only net external force will be the force F. The interacting force between the two bodies, namely the tension in the string, will not be the external force, because this is the force between the object within the system. So the force T1 and T2, the tension force, is the internal force. And the force F, which is acted from outside the system, is called the external force. Okay. Now, but we can define the system differently. We don't need to define the system in this way. The system is chosen by us. So we can choose to define the system as only including the mass M1. And in this case, the force F is obviously external force, but also the tension in the string is external force. Why? Because we only include the mass M1. And the tension force is due to M2, which is outside the system. So it is external force. It is external force that is pulling M1 backwards, right? So in this case, both F and T1, they are the external force. So when we apply Newton's second law, we should always find the vector sum of the external force, and that gives us a net force, and then we k the net force with the mass time at the acceleration of the system. And in this case, in the first case, the mass of the system is a sum of the mass of the two bodies, because we include both bodies, right? And in the second case, the mass of the system is simply the mass M1, because the M2 is now excluded. Okay, so be careful when you apply Newton's second law. And there are many kinds of common force. The first kind of force is gravitational force, and is always directed towards the center of the Earth. Or if you are in other celestial body, the gravitational force will be directing to the center of that gravitational center of those body, like for example, the sun or the moon. Now the tension force acts along a taut string or spring. Okay, so if you place an object on an inclined plane, the weight of the body will be vertically downwards towards the center of the Earth. And if you are pulling this body up along inclined plane, there's a tension force in the string, okay, acting on the body. And that may be also the normal force. The normal force, or sometimes called the normal reaction, acts in the normal direction to the surface. So if I place the block on the inclined plane, I will find that the normal force will be acting in a direction perpendicular to the plane. And that's why it's called normal. Normal means perpendicular to a surface, okay? And what is friction? Friction is a force that tends to oppose the relative sliding motion. If you are pulling this block upwards, then the frictional force will be the tangential force that tends to oppose the motion and is directed downwards along the plane. So the frictional force tends to prevent this body from moving. Okay, so that is the frictional force. Now, I must clarify a misconception about friction. Somebody tells me that friction is a force that always prevent motion, that always oppose motion. Now, this is not always true. Now, why? Now, imagine now I have the wheel of a car rolling forward like this. In this diagram, is rolling forward in the anti-clockwise direction. So imagine you have a car, and now I can see the wheel of a car rolling forward in the anti-clockwise direction. So how would the car move? Do you know? Now, if you consider a rotation of the wheel in this way, there would be a frictional force applied by the wheel on the ground, right? And the frictional force is in the backward direction because the wheel is rotating this way and it's rubbing the ground, right? So it rubs the ground this way. And so it applies a frictional force backward on the ground. And by action and reaction, the ground also applies a frictional force on the wheel. And that frictional force is in the forward direction. Can you see that? So this forms an action and reaction pair in Newton's third law. The tire rub on the ground, producing a friction backward, but the ground also produces opposite friction on the wheel, pushing it forward. It is the frictional force acting on the wheel that propel the car forward. Okay, now this is the only net force that propel the car. Okay, there's no other forces that propel the cars horizontally along the road. So in this case, the frictional force is the driving force of the car. It is not the force that preventing the motion, that is opposing the motion. Is not. It is actually the driving force of the car. So what is wrong about this? I think it is wrong to say that the friction always opposes motion. But it is true to say that the frictional force tends to oppose relative sliding motion between the two surfaces. Now, you can see here, even in here, the tire tends to rotate in this direction, right? And it tends to slide over on the road, right? But the road produces a frictional force to oppose that. Okay, so the frictional force actually tends to oppose the sliding motion between the two surfaces. Although it provides the propelling force for the car, it tends to oppose the sliding motion. It tends to prevent the type from sliding over the road. Okay, so it's correct to say that the friction tending to oppose the relative sliding motion between the two surfaces. That is a true, that is a correct statement. Okay. Now, in your high school physics, you may learn about contact or non-contact force. The push and the pull are the contact force, the gravity force, the magnetic force, and then they act over a distance, and that's called the non-contact force. Now, in senior level physics, I tell you that there's no such thing as contact or non-contact force. In nature, only four kinds of force exist: the electromagnetic force, the gravitational force. I think you already know the first two, and there are strong force and weak force. The strong force and weak force act in the atomic nucleus. Okay, this is the subatomic world kind of force. Do you know what kind of force bind the nucleon together in the atomic nucleus? Now, you know that the atomic nucleus consists of proton and the neutron, and the proton carry positive charge. So the positive charge of the proton will be repelling each other. So without any other kind of force gluing all the particles together in an atomic nucleus, the nucleon will be scattered by the strong repulsive force due to the electric charge, right? So that must be a kind of force that glued all the particles together. And that kind of force is a strong force. The strong force is a strong attractive force that stick the nucleon together inside an atomic nucleus. And the weak force is responsible for many important nuclear process, like for example, the beta decay. The decaying process is sometimes mediated by this kind of weak force, but they are the force that you don't commonly see in your daily life, but they are at work in the subatomic world. 20 years ago, there was an old professor in Chinese University. His name is Chen Yuhua. He always said that 人有悲歡離合，力有電重強弱。水調歌頭，蘇軾水調歌頭，月有陰晴圓缺。但 what he say is 力有電重強弱。What he mean by 電重強 is the electromagnetic gravity strong and weak interaction. Okay. The long lecture, and so I let you have a break for 10 minutes. Am I recording? I also would like to have a review with you on Newton's third law. I think you know what is Newton's third law. It says that when two bodies interact with each other, the force acting on the bodies are always equal in magnitude but opposite in direction. So imagine now you have two bodies A and B. For example, in this example, they are tied together by a string. In that case, the force pulling on body B and the force pulling on body A, they are equal in magnitude, but they are in opposite direction. So in vector form, we may write FB vector equal to minus FA vector. The vector sign means now I consider also the direction. So if they're opposite, there should be a minus sign. Okay, there should be a minus sign in the equation. Now this two forces is called an action and reaction pair. Now there's actually no distinction between action and reaction. You can call any force the action, any other force the reaction. The two forces actually happening together. They arise together. You cannot distinguish which one is action and which one is reaction. Okay. And the important thing is that the two forces must be applying on different body. Okay, they are due to the same interaction, but acting on different body. And they never will be the same on, they will never act on the same body. Okay. Now let's just discuss a simple example of the action and reaction pair, of identifying action and reaction pair. That is the tug of the war game. Now suppose at a certain instant, person A and person B, they are pulling each other. They are playing the tug of the war game. They are pulling each other through a string. And at this instant, they are at rest. So what are the forces acting on the body? So I can name four forces. The two forces must be the string, the tension force in the string, right? The force pulling body A, which I call FA, the pulling body B, which I call FB. They are the force coming from tension on the string. But there are also two forces from the ground. Because the two persons are not moving at this instant, so there must be frictional force on the ground that oppose the motion. And the frictional force are called GA on body A and GB on body B. Now we know that all the forces are equal. In fact, the magnitude, in terms of the magnitude, FA, FB, GA, GB, they are all equal. But they are equal for different reasons. Now, the first thing is that we know that FA is equal to FB because they are the action and reaction pair. Okay, they are due to the interaction of A and B. Direct interaction, the direct pulling force, direct pulling of it towards each other through a string, the same interaction. But they act on different body. FA act on body A, FB act on body B. So there's a pair of action and reaction. So this is by Newton's third law. The two forces are equal. Okay. Now, but if we isolate person 1 or person 2 from the rest of the world, we will know that FA is equal to GA and FB is equal to GB. Now, these two pair of forces are equal, not because of Newton's third law. They are equal because of Newton's second law. If you consider body A, for example, the net force acting on him is GA and plus FA. And this two force has to be cancelled because body A is not moving. By Newton's second law, if body A is not moving, the net force acting on it must be 0. And that means FA must be balancing GA, right? The two forces must be cancelling each other. And similarly, FB must be cancelling with GB. They must balance each other. Okay, so these two pair of forces are equal by Newton's second law, and the condition that the two persons are not moving. Okay. Now, but if you consider FA and GA and FB and GB, they are not action and reaction pair because they act on the same body. Okay. FA and GA both act on A, FB and GB both act on B, so they are not action and reaction pair. So when you say the forces are equal, you should have a reason, and you should distinguish between whether the forces are equal by Newton's second law or Newton's third law. They are conceptually different. Okay. Now, after a long lecture, I would like you to answer my question now. Suppose a person is standing on the ground. How many forces are acting on the person and also the ground due to the interaction? Okay, I now label all the forces on the person and on the ground. So what are the relationship between these four forces? Okay, which two forces are action and reaction pair? You should be able to identify two pairs of action and reaction. And the other force will be equal by Newton's second law, right? So what are they? Anybody answer me? You're all sleeping, right? After a long lecture. Or you just disappear from the screen to do something else. Somebody answer me. R and R prime are what? R and R prime are what? Do you mean action and reaction? Yes, yes, you are correct. Now the action and reaction actually they are R and R prime. This force and this force, they are the action and reaction. Now these are what kind of force? They are the contact force between the person and the ground. The person press on the ground and the ground support the person. It's due to the interaction, right? So they are equal and they form a pair of interaction between the person and the ground and the earth, okay? Due to the contact between the two bodies. But there's also another pair of forces. The person, the earth exerts the force of gravity on the person, right? And that is the weight of the person. So it's pulling the person downwards. But at the same time, the person is also pulling the earth with this equal and opposite force, right? Although this force is negligible because the Earth has a very large mass, but the force is still there, okay? And so they form an action and reaction pair. This is due to gravity. And the first one is due to contact, right? They are of different nature, you can see. The first one is due to the contact interaction, and the second one is due to the gravitational interaction. So when you identify an action and reaction pair, you should identify the kind of interaction between the two bodies first. Normally, we find different action and reaction pair correspond to different different interaction. Okay. Now, also we find that by Newton's second law, R is equal to W because the person is at rest, right? And of course, the Earth is also at rest. So R prime is equal to W prime. So these two pair of forces are equal because the body are not moving. Okay. So here is the answer. Now we then would like to introduce to you how to use free body diagram. The first thing is to choose a body and isolate that body from the rest of the world. For example, if I choose body A, then I draw a rectangle to enclose body A, and I can see the external force acting on him are GA and FA. If I isolate body B from the rest of the world, then I draw a free body diagram for B, and the external force acting on him is FB and GB. Okay. But I can also include more than one body in the system. Suppose I include both A and B in our system. So I enclose A and B as a whole. Okay, so you can see I draw a rectangle to enclose both A and B, which means that they are counted as a member of the system. In that case, the pulling force between them is the internal force. And if I apply Newton's law on them, then I should count only external force, which are the force from the ground. The force from GA from the ground on A and the force from ground on B, GA and GB, they are the external force. Okay, so be careful when you identify the external force and internal force. They depends on your system, on the system you choose. Now, inside Newton's law, there's some internal consistency. Let us consider this system. Two blocks being connected together by a string, and there's another string pulling block A to the right. Okay. Now, if we take a free body diagram of body B, if you make a free body diagram of body B, the only external force is TB, the tangent force, right? The tangent force from A acting on B, that is I call TB. And so if you apply Newton's second law, TB will be equal to MBA, where A is a common acceleration of the two blocks. Okay. Now, if you apply the free body diagram on body A, then you will find the force F and the tangent force TA, they are both the external force. So because they are in opposite direction, so you have to add a minus sign to TA. So I have F minus TA equal to the net force, and the net force is equal to MA multiplied by A, acceleration. Okay. Now, if you add up these two equations, and you assume that TA is equal to TB, and of course they are equal by Newton's third law, right? They are a pair of action and reaction, so they are equal by Newton's third law. If you add up these two equations with the condition that TA is equal to TB, then they just cancel on the left-hand side. And you will find that the force F is equal to FMA plus MB multiplied by the acceleration A. But this is exactly the Newton's second law applied to to the two body as a whole. Why? Because if we assume that now the system includes both body, the total mass of the system is ma plus mb. And the only external force acting on the system is F. Is that right? The internal force doesn't count. They are internal interaction. And when I draw a free body diagram, including the two body, the internal force between the members of the body doesn't count. And so I only have only one external force, that is F. So the equation of motion with F equal to ma plus mb multiplied by A. But that's exactly the same equation produced by the first consideration, right? So they are identical. Now, the consistency between these two sets of equations hinge on the fact that TA is equal to TB. If Newton's third law does not hold, if TA is not equal to TB, then applying Newton's second law to each of the body will be different from applying Newton's second law to the two body as a whole. That will be self-contradictory result. So that means what? That means Newton's third law is important to maintain the internal consistency when Newton's second law is applying to different free body diagram. Okay, so without the Newton's third law, Newton's second law cannot be consistent with itself when it's applied to different free body diagram. So that's why Newton's third law is important to be there. Okay. So I just want you to see a deeper aspect of the Newton's law. They are interconnected with each other. Their internal consistency between Newton's third law and Newton's second law together with different free body diagrams. Now let's just handle a simple problem. It's not quite simple, but it's quite interesting. I think we have a trolley. The mass of the trolley is capital M. And now I have a horizontal force pushing the trolley, making it accelerate forward. Okay, but on the top of the trolley, there was a mass M1. Okay, and the mass M1 is free to slide over the top surface of the trolley without friction. But the mass M1 is connected through a pulley over the trolley to another mass M2, which is hanging before the trolley. So the mass M1, M2 can move vertically while pulling the M1 downwards or retreating it upward over the string of the pulley. Now our problem is like this. Our problem is I want to find a force F that can push the trolley such that M1 and M2 are at rest relative to the trolley. I don't want M2 to fall down. I don't want M1 to be pushed to be pulled forward or leaving behind by the trolley. I just want them to move together with the trolley at the same acceleration. I don't want any relative sliding motion between any of this body. So I want to find the force F that can satisfy this equation, that can allow the free body moving together forward with a common acceleration. That is our goal. Okay. Now let's separate the problem into three body diagram. Okay. I can separate the mass M1 from the rest of the world. And the only force that is pushing, this is pulling the block M1 is the tension. I call this tension T1. Now I neglect the vertical force because I know the vertical force must be balanced anyway. So I don't draw the vertical force to simplify the diagram. The vertical force are there. The normal reaction actually cancel the downward force of gravity. But that is not involved in this solving this problem. So I just simply neglect that. Now the tension force T1 is producing acceleration on M1. So T or T1 is equal to M1A. Okay. So it is an acceleration forward, the common acceleration of the free body. Now let's take a look at the block M2. Now be careful, the block M2 is acted by three forces. The first one is of course the force due to its gravity, its weight. and that's M2G vertically downwards, and there's a tension on the string, and there's also a pushing force from the cart, from the trolley, right? And I call the pushing force from the trolley R. Okay. Now I know that the tension from the string T2 is equal to T because the pulley is frictionless and the pulley is very light. So I suppose the tension to be the same throughout the whole string. And so T1 and T2 are both equal to T. Okay. So the vertical motion of the block M2 is 0 because there's no vertical motion. I do not allow the block M2 to descend or ascend. I want it to remain at rest at this position. So the vertical motion is 0, and then I have M2G be equal to T. The two forces balancing each other. But horizontally, there's an acceleration. The horizontal acceleration is due to the pushing force from the trolley. So R is equal to M2A. That is a horizontal equation of motion. Okay. So I now have 3 equations. This one, and this one, right? So what is the 4th equation? I can apply a free body diagram for the whole system. I regard the free body as a whole being acted by the external force F. So in that case, the external force will be equal to the mass of the whole system, which is M plus M1 plus M2 multiplied by the common acceleration. Is that right? Now, how do I find A? Well, I can find A by looking at this 3 equation. Now, from the first equation, I know that M2G is equal to M1A because the T are common, right? So M1A is equal to M2G. And that means what? That means A is equal to M2 over M1G. Is that right? So I can substitute this A into this equation to find the force F. So now I arrive at my answer. The force F is the sum of all masses multiplied by M2 over M1G. So this is my result. So I need such a force in order to maintain the free body moving together as a whole. Okay. Now in this case, we have applied Newton's second law to the free body as a whole, right? But you may ask a question: can I isolate the trolley from the rest of the world to draw the free body diagram for it? Can I use the trolley itself as a free body in a free body diagram to set up the equation to solve this problem? Yes, you can. The answer is yes, you can. But it's rather tricky. You must be careful when you draw the forces. Now let's take a look at the trolley. Now the pulley belong to the trolley, is part of the trolley actually. So the pulley is actually acted by the 2 forces. It's due to the string. The string has a tangent force. On this side, the tangent force is pulling the pulley backwards, and on this side, the tension is pulling the body downwards. So there's 2 tangent force here, and there's a normal reaction force from the block M2, right? The force M2 has a normal reaction force R acting on the trolley, and of course the pushing force F, right? Now, so I can apply the balancing of force in the horizontal and apply Newton's second law to the trolley in the horizontal direction. So what would be that? F minus R is backward, and also this T is backward. So RF minus R minus T is the net force in the horizontal direction. And that should be equal to the mass of the trolley multiplied by the acceleration, right? But I know R and T as before. R is given by M2A and T is given by M1A, right? So I put back R and T into this equation. And when I move this 2 terms to the right, I get the same equation as before. And after inserting A as M2 over M1G, I get the same result. Okay, now you can see it is a little bit tricky if you want to apply the Newton's second law to the trolley. If you want to draw a free body diagram for it, it's quite tricky. But if you are doing it carefully, you can still arrive at the same result. But of course, it would be much easier for you to apply the Newton's second law to the body, to the free body as a whole. There will be a simple equation as result. I have a classwork for you. Let's see if you can do it. Okay. Now, in the previous example, we have a free body. Now consider two. I consider a block rests on a wedge. The wedge has a plane inclined and an angle theta to the horizontal. So the wedge and the block, they rest on the horizontal table, which is smooth. And now I have a force F pushing the wedge horizontally, such that I want the block to be at rest relative to the wedge without sliding down. So the block and the wedge actually move together to the right with the same acceleration A. Okay, so in this problem, I want you to find F. I want you to find out the force required to keep the block at rest on the inclined plane of the wedge. Now I have some hints for you. I want you to consider the free body diagram of the block. And I resolve the normal force R, the normal reaction R from the inclined plane on the block into two components. R cosine theta is a vertical component, while R sine theta is a horizontal component. Okay. This angle is theta, is equal to the angle between the inclined plane and the angle that the inclined plane make with the horizontal. Okay. So and also you can apply the second law to the block and the wedge as a whole. Okay. So after solving this three equations, you should be able to find the force F that can produce a common acceleration A on both bodies. Okay. Can you do it now? I give you 3 minutes. Okay, you just write down this three equation and solve for F. When you know the answer, please don't be shy. Just let me know, right? You just type something on. You just type something on the chat box to let me know that you are with us. You are doing a problem with me. Okay. Oh, somebody answer me. M plus, yeah, you got it correct. Great. Any other student who have finished the calculation? Please let me know, okay? If you have difficulty, also let me know, okay? All right, let's do it together. Now, this is R, right? So R sine theta is a vertical component. Now, I claim that, sorry, I made a mistake. R sine theta is a horizontal component, right? It's this component. That is R sine theta, right? And R sine theta is exactly producing the acceleration. And the common acceleration of the block and the wedge is A, right? So it shared that this is acceleration shared by the mass, by the block, right? So I have R sine theta equal to M8. Is that right? But how about R cosine theta? R cosine theta is a vertical component of the force. It is this component. Now, is the block moving upward and downwards? No, the block is moving. Sorry, any comment from you? The block is moving horizontally. It moves horizontally together with the wedge. It's not moving up and down, right? So there is no vertical motion for the block. And if there is no vertical motion, that means the vertical component of the force are balancing each other. So that means R cosine theta should be balanced by the force of gravity. And that's mg. And if I apply Newton's second law to the block and the wedge as a whole, the total mass of them is m plus mg. Well, m plus m, the total mass of them, right? And the common acceleration A. So, right? So F is equal to m plus ma. It is the Newton's second law applied to both the block and the wedge as a whole, right? Now you can see from this equation, from equation 1 and equation 2, if you divide equation 1 with equation 2, you'll find that the R will cancel. And A over G is equal to sine theta over cosine theta, and that is tangent theta. So you now know A. A is just G tangent theta. So the force that is required would then be equal to big M plus small m, G tangent theta. Now I would like to ask if this result is reasonable. Is this reasonable? I would like to ask this question. Now, I think you should always check whether your calculation result is reasonable. For example, I can take some limiting case. For example, I can take the case where the wedge is nearly horizontal. When theta is very small, what will happen? When theta is very small, that means the inclined plane is almost horizontal, right? So the block is actually at rest on the horizontal plane, right? You don't need a force to keep it at rest. So the force required to keep the block at rest on the plane is 0, right? And so that is reflected from this tangent theta factor. Okay, when the theta is 0, tangent theta is 0. So I don't need any force to maintain the block at rest on the plane. Okay, but how about if theta is 90 degrees? If theta is 0, then F is 0. But if theta tends to 90 degrees or pi over 2 in radian, tangent theta become tending to infinity, and the force will tend to infinity. Is this reasonable? Normally, we will not encounter infinity in our solution. Is this possible? Is this reasonable? Yes, this is reasonable. Imagine now the wedge is so inclined that it's almost vertical. So we have a vertical instead of an inclined plane, we have a vertical plane. So the vertical plane is now pushing the block forward. Okay. But there's no way for us to control its vertical motion. Without friction, the block will obviously slide down along the vertical plane, right? So there's no way for us to control it because the force from the plane is already in the horizontal direction, but not in the vertical direction. So that means you need the infinite force for that to happen. When you are having a plane that is more inclined, the force acting on the block will be more in the horizontal direction with less swing force in the vertical direction. So you need a very large force to keep the block at rest on a very steep inclined plane. So that means you have a solution blowing up, tending to infinity. And that is reasonable, actually. Okay. I would like to ask a question. In this example, I resolved R in the vertical direction and the horizontal direction. You may be tempted to do the otherwise. You may be in your high school study, the teacher may ask you to resolve the force component along the plane and perpendicular to the plane. So you may be tempted to write such an equation. If you resolve the weight mg in a direction perpendicular to the plane, you may be tempted to write R equal to mg cosine theta, right? Because these two forces may seeming to balance each other, right? Have anyone tried to do that? I think so. I think some of you might have done that. Okay. Anybody raise your hand? Now this equation is not correct. In this case, I would let you see why. If you write mg cosine theta equal to R, it means that there is no motion in this direction, in a direction perpendicular to the plane. But that's not the case. Because the block is now moving horizontally, and the direction that is normal to the plane and the horizontal direction, they are not in right angle. So when the block is moving horizontally, there is actually a component of acceleration along the direction perpendicular to the plane. So that means along the direction perpendicular to the plane, the forces are not balanced. The force components are not balanced in that direction. So you cannot equate R with mg cosine theta. Okay, but you can equate R cosine theta with mg because you know the block is not moving vertically. Okay, so that is different. So there's quite subtle difference here between R cosine theta equal to mg and R equal to mg cosine theta. Okay, if you don't understand this point, I welcome a further discussion. Okay. Now then we come to a vertical circular motion. We don't have much time now, but hopefully I can give you some idea of what circular motion is. Now, you learned horizontal circular motion in high school. Now we make this circle along a vertical plane. Okay, we swing an object so that it instead of moving in a horizontal circle, we move the circle. We swing the circle in a vertical plane. Now, so the object is there, and at different points on the circle, the direction of the tangent force and the direction of the weights, they are making different angle with each other. Suppose the object is directly below the point of suspension, directly below the center of the circle. The weight of the object will be vertically downwards, but the tangent force from the string will be directed towards the center of the circle, right? Because the string providing the centripetal force, right? So the tangent and string is directed towards the circle, the center of the circle. So the two forces are in opposite direction. And if this instant the body is moving with a velocity v, then T minus mg, because the tension force need to be larger than mg to provide the centripetal force. T minus mg is the net force, and that is the centripetal force. And by high school formula, the net force in a circular motion is a centripetal force, and that centripetal force is mv squared for r. Okay, so T minus mg is mv squared for r. That is the formula you learn in high school, the centripetal force formula. Okay. Now, but how about if the body is at the top? If the body is above the point of suspension, then what will happen? Now, you can see that the string is now pulling the body downwards, and the gravity force is also pulling the body downwards. So they are in the same direction, right? So instead of a minus sign, you have a plus sign, because both the tension and the weights of the object, they are producing the centripetal force. They added together to produce the centripetal force. So T plus mg is the net force, and the net force is equal to the centripetal force mv squared r. And how about at an angle? If the string now makes an angle theta with the vertical direction, so how do we write down the equation? Well, we resolve the force component along the radial direction. That is the direction towards the center of the circle. The tension T is of course towards the center, no problem. But we have to resolve the gravity, the weights of the object along this direction also. And this produces a component of mg cosine theta. Mg cosine theta is the outward direction, outward component of the weights. Okay. So the equation reads like this. The tension force minus the mg cosine theta, because they are opposite direction, is equal to the net force. And the net force is of course the centripetal force mv squared of r. Now in these three cases, although I write the same v, in fact the t and the v, they may be different. Okay. In some position, the t may be larger, and in some position, the t may be smaller. And also the v may vary, it depending on how you swing the object. Okay, different swinging method will produce a different t and different v. But as long as you are at a given position, these three equations are always hold. For example, if you have at a general position, you always have t minus mg cosine theta equal to mv squared over r. Okay, and if you are at the top, you have this equation, and if you have at bottom, then you have this equation. Okay. Now, how about a roller coaster looping? For example, if you have a roller coaster going around a loop, and the roller coaster is now at the top of the loop, then what is the force balancing? Now, I know that the roller coaster is being acted by the trail. Okay, the rail will exert a force on the roller coaster. And I denote this force by the normal reaction N. The force is exerting on the roller coaster downwards. So together with the weights of the roller coaster itself, they produce the net force, right? And the net force is a centripetal force, mv squared over r. Now, if I should keep, in order to keep the roller coaster attached to the rail, the normal reaction should be larger than 0, right? If the normal reaction is 0, that means the roller coaster is detached from the rail, and that would be danger of the roller coaster falling down, right? I don't want that to happen, right? So in order for the roller coaster to attach to the rail firmly, I need the normal reaction to be larger than 0. And if I need n to be larger than 0, I need the rail to attach to the roller coaster. Then what I need is mv squared for r be greater than mg. So I need a high velocity. So I need to let the roller coaster to slide down from a very high altitude, so that when it goes through the loop at the top, its velocity is high enough such that mv squared over r is larger than mg. And in that case, and the normal reaction force will be larger than 0, and the roller coaster will be firmly attached to the rail without falling down. Okay, so that is the idea. Now, before letting you go, I let you have a simple experiment. Look at me now. Don't look at the PowerPoint slide. Now, I have some water here, right? I have some water here, and I put it on a stand. I don't have glue on the stand, so it's loosely attached. So now I swing it in a vertical circle. Now I have the whole thing inverted, okay? But the water doesn't fall down. Why? The same reason as this. Now when the cup is inverted, the cup is exerting a normal reaction on the water. And together with the weight of the water, they provide a centripetal force. And so N plus mg is equal to mv squared of R. If I swing it sufficiently fast, if V is sufficiently large, then mv squared of R is larger than mg. And that guarantees that the normal reaction due to the cup acting on the water is larger than 0. And that means if I swing it sufficiently fast, then the water will always be attached to the cup without falling down. So that's why the water doesn't fall down, right? Because it's firmly attached to the cup and because N is larger than 0. Okay, now this is a simple demonstration. And in the next lecture, I will show you this example. I will show you a so-called centrifugal track, bead sliding down from a great height, and it goes through a circle here. And then I want you to find at the maximum heights the velocity and also the condition that the bead can go through the whole turning of the circle. Okay, so let's stop here. If you have any question, please ask me now. I stop the recording first.